model selection. Here's my outline. And I thought I would start with something really simple and almost boneheaded. And that is just the relationship between two variables, like relative horn length, relative wing length. What's the association? These data come from the Doug Enlin paper on the relationship between body size and horn size in male beetles of this species. And you know, the question that I want to use this data for is very simple. What's the best model? That's the theme of the paper and the discussion earlier, and I want to ask it in a very simple context, just to say that actually it's kind of the same. This is the same problem. Normally, and what we might think of doing is just a linear regression, simple model, fitting the relationship with a straight line. But often we ask ourselves, well, is the relationship actually linear? Maybe it's curvilinear, and we might be able to describe that with a quadratic expression. So it's a slightly more complicated model, but hardly biologically unrealistic. So that's a polynomial degree 2, and as I was, preparing this lecture for the first time, I thought, why stop at 2? I get a 3rd degree polynomial of these data, and I like it. Degree 5 is also pretty good. And even though there's 10, I couldn't fit the whole curve on the page. It kind of shoots up there, turns around, and comes back down. And the reason I show you this is really to address the question, how do we know which model is best? Like, how do we objectively make that decision? Well, we might say, let's choose the model that has highest R squared. Or let's choose the model as the highest log likelihood. Okay, here's the relationship between log likelihood and the degree polynomial. It just goes up and up and up. Here's the R squared. Isn't that what we want? We want to fit the data better and better and better. Well, 10 degree polynomial. Actually, 12 is even higher than 10 for a degree polynomial. So I asked the question, is this good? This is one way to answer the question, how do we decide objectively which degree polynomial to fit to these data? Well, log likelihood is perhaps one of those methods. Does it give us what we want? But at the same time, when we look at this picture, we think that there's something wrong with it. I can't put my finger on it, but I know this is wrong. Without looking ahead on the slides in front of you, why is this wrong? What makes you think that this might not be a good idea to fit a really complicated model to these data?
I would just take a stab at it. I just feel like I can't see any relationship or trend within that. It just becomes, I think, so complicated that I don't know what the takeaway of it is.
So it's just too complicated. You feel it's too complicated. Well, why is that a problem? Highest log likelihood, remember? Should I show you the slide again?
Listen. Go ahead. This possible thing, you can't even see the whole model.
That's a problem, but we can zoom out. Simple fix.
I was going to say, does it have to do with using the model to predict more data points?
Did you look ahead?
No.
So that is a potential problem. What we want to fit data with, the model we fit the data, we have some sense that these data are kind of ephemeral. We might go back to the same population, and that this model might not actually do a good job predicting the next data point. But how do we decide that objectively? And one way in which this has been done in the past is to just, it's too complicated. Because we think that maybe biology is simpler, which was one of the points that came up in the discussion. And this sort of led to the point of view out there that models should be pared down until they are minimal adequate. So the idea of a minimal adequate model, it has come up already, and the conventional way of doing that is to throw out all terms that are not statistically significant at a 0.05 level. And Crawley, 2007, that's the R book where he actually promotes this idea. And the method that's often used to pare the model down to size is stepwise elimination, for example, as was presented in the talk. And that's the conventional method, and that's the method that Crawley in the R book actually promotes. But we read the paper and had a discussion to learn that there are some issues with this. What exactly does this minimum adequate model do for us, and why is it the best? How do we decide what model is best? So the trouble with stepwise elimination of terms, backwards but forwards, and then bidirectional has the same problem. In the stepwise elimination process, every time a variable is dropped, you accept the null hypothesis, as was pointed out. You assume that the slope of the coefficient beta is truly 0, which seems somewhat unlikely. And so what happens if we make a mistake? What if there's an error along the way where we accept the null hypothesis, but it's actually false? What does the minimum adequate model do for us then when we know that the chance of making a mistake is high, particularly when there are lots of variables? In what sense do we end up with the best model? And a question that also comes up with this approach is how repeatable is the outcome of stepwise regression? If we went back to another sample, would we end up with the same best model? And if not, what do we do? So the reading addressed that by fitting different, or repeating the process in different years and showing that the outcome is different each time. And finally, the point came up again that stepwise regression gets us to a minimal adequate model, but what is the uncertainty associated with that? How do we describe that? And normally when we calculate an estimate of something like x bar, we append a standard error, and that's a description, or a confidence interval, that's a description of the uncertainty associated with that estimate. But we don't actually have such a number for the minimum adequate model. What is our certainty? What's the standard error of the best model? Well, part of the reason why we have trouble doing that is that this wasn't actually selected using a very explicit criterion. So the point came up that the really complicated model might not do a very good job predicting the next observation. And so a reasonable criterion is to choose the model that actually does predict best. And one way that we can do that is with the data at hand and using something called the cross-validation score. So a cross-validation score is where you fit you drop one method is you take one data point and you leave it out. You fit your model, and then you see how well that data point is predicted by the model. And the difference between the prediction for that missing data point and the actual observation is called the prediction error. So epsilon squared I is the prediction error for observation I when it's left out. The model is fitted, we put it back in, and then calculate square the residual, essentially, the prediction error. And then we do that one at a time for every I, for every observation. And then sum those prediction errors, those squared prediction errors, into something we call the cross-validation score. Okay, so the epsilon I is the difference between the observed observation and the predicted observation when that observation was left out of the model, squared. Okay. And so a larger CV score means a worse prediction. So here's the relationship for my simple example of regressing beetle horns on body size. So the cross-validation score is plotted against the degree polynomial, and remember, high score means poor prediction. So what's the best model in this case? The first degree polynomial, a linear regression. So that's your goal, is to predict, to be able to fit a line or fit a relationship that has some generality to predict the next observation. Then a linear regression is your best bet. The second thing I want to point out with this example is that a quadratic is almost identical. So how do we choose between them then? This is the best by this criterion, but actually, we did this kind of analysis, we'd be able to say actually all the way up to 5th degree polynomial does reasonably well. And amazingly, 9th degree polynomial has an impressive cross-validation score. And I'm pointing this out here again just to show you the dangers of data dredging. Even though we're searching for a model that best predicts, given the data at hand, we're still data dredging. I have no hypothesis in here as to what the relationship should look like. I'm pretty sure, though, that the real relationship, if it is a 9th degree polynomial, most of those coefficients are pretty small. So it seems unlikely. I don't have very much confidence that if we actually did go back and calculate or collect a new sample, that this degree polynomial would do that well. So this simple example illustrates some of the issues that we have when trying to decide the best model. And data dredging is going to be a problem with all the methods that we have, just because data dredging will often discover things that are completely artifacts of repeating a procedure over and over again. You're going to get lucky, but it's going to be an artifact. And the model selection methods that I'm about to tell you about don't actually cure that problem. Okay, so why do these more complicated models make prediction errors in the first place? Well, the intuitive answer would be, well, they make prediction errors because they're actually wrong. But that's not exactly right. Complicated doesn't necessarily mean that the models are wrong. Prediction error itself results from a combination of two things. And simple and complicated models have opposite effects on these two things. And this trade-off is known as the bias variance trade-off. And it goes like this. The simplest model, like an absolute straight line between horn length and body size, is unlikely to be truly correct. But the relationship is precisely linear. A line might do a pretty good job of predicting, but if the relationship is actually quadratic or even a little bit more complicated, fitting a simple model might be fine, but it's going to be biased because it hasn't included those other terms, which might be real even if their effects are small. So an overly simple model is likely to be biased because essentially we're dropping terms. So the best way to minimize bias is to fit the most complicated model possible. Now that sounds strange, but the idea is we can fit a 10th degree polynomial, and if we fit a 10th degree polynomial to data, we will get an unbiased estimate of what all those coefficients are, even if that true value is 0. So if the true value for all the higher order coefficients is truly 0, fitting a 10th order polynomial to the data is going to give you an unbiased estimate of that. And by that I mean, if we were to repeat the sampling process and fitting over and over again under the same circumstances, eventually we would take the average coefficient that we get from that process and it would be 0. It would actually be the correct answer. And so the most complicated model is actually the one to use to minimize bias. However, the most complicated model has another problem, and this is where most of its prediction error comes from, and that is the sample size is not very large and your estimate of the coefficients for that 10th order polynomial are terrible. In one sample you'll estimate it to be large, the coefficient associated with the 10th order term. Go back to the population, take another sample, the next time you'll estimate it, it'll be negative and large. Its true value is 0, but every time you sample, every instance in which you sample and then get an estimate of the value is a terrible estimate. So that's called variance. So prediction error can be high, your prediction can be terrible because your model is biased, or because your model is unbiased, but you have high variance. And somehow, what we need is some way in which those bad things are balanced to produce an outcome, a model, that when fitted to data we can say is the best in some way. Here's a simulation kind of this process. It's a pile of simulations relating prediction error to model complexity. And what the person simulating the data did was, the model was known, and there were lots of terms in it. And when fitting a complicated model, so the observation in that case is that the more complicated models, the lower the prediction error for the simulated data. But what the person did was, every simulated data set produced from a model of known complexity, every time a simulated data set was created, it was divided into two parts. And the first part was used to generate this curve, how well does it actually predict the data at hand. The red curve is how well did it do predicting the other half of the data. And so more complicated models predict the data at hand better and better. Log likelihood goes up enough. I showed you that already in my simple example. But when you try and predict the other half of the data, you find that there is a point at which the prediction error is minimized and then it goes up again. And that's the point at which this bias variance trade-off is reconciled. I already mentioned this, and that is that my polynomial regression analysis is data dredging. I didn't have a hypothesis to guide my search, and that point came up in the presentation earlier in the form of, have a theory and use data to distinguish between possible theories rather than just, behave in a manner analogous to the cartoon that was shown at the very beginning of the talk, where you shoot at the target and then you draw the target around the holes. Do you guys follow XKCD? I don't know who this person is. I've never looked up his biography, but he has an uncanny understanding of what we do here as scientists. So this is a scatter plot of data and different curves fitted to those very same data and what they mean. Look, it's tapering off. Look, it's growing uncontrollably. Probably there is no good fits to the data. It's disturbing how much this person, this comic, knows. So, I want to sort of visit the problem from scratch. What are our goals when we fit models to data? And just about every analysis that we do involves fitting model to data, even calculating an average. Has an LM formula associated with it. It's fitting a model to data. So here's some reasonable objectives to achieve. And the idea is, what is the method that will help us to achieve these goals? Well, one is, it would be great if we had a model that predicted well. So that point came up, and we used a cross-validation score that found the linear regression was actually the best predictor in this case. We would also like a model that approximates the true relationship. In other words, we don't just want to predict. We actually want a model that is right, is correct in some way. I have bad news for you, but at least an approximation would be satisfying enough. Another thing is, we would like to know what other models fit the data nearly as well, so that we have some sort of idea of uncertainty. That we could say, here's a set of models. Here's not just X bar. Here's a set of possible values for X bar. Plus or minus standard error. A 95% confidence interval for the estimate. Can we do the same for models? Yes, we can. And secondly, this is maybe not one that you have dealt with, but one that we'll deal with in the workshop this week, and that is to compare models that are non-nested. So all of the methods that we've used so far, in linear models, using f-tests, in generalized linear models using log likelihood ratio tests, we've always compared a full model with a reduced model. A full model contains the term of interest. The reduced model lacks that term of interest. Those two models are nested in the sense that everything in the reduced model is already contained in the full model, plus there's some extra terms. But the methods that I'll tell you about can also compare models that are not nested, that have exactly the same number of parameters, or that have different variables in them entirely. So I already talked about CV score, and now I'll talk about AIC. And I won't have time to talk about BIC. It's another information criterion. It'll come up in the third assignment. But there's kind of two components then to achieving these goals, and one is to come up with an explicit criterion, and then the second is to come up with a strategy for finding the best model that meets that criterion. And R has tools to do this once we have made a decision about our criterion. Typically when these methods are used is when we're modeling observational data. We want to predict how many salmon are coming back next year based on all of the data on temperatures and other environmental variables that have been measured in years past. These are observational data. We don't have an experiment. We might have built a theory and have some idea of what variables are important, but we don't really know, so we're going to have to do a bunch of model comparison to figure out what's the best. But often experiments are carried out to compare the fits of two models to data as well. When you do an experiment, often, well, I've already promoted the idea that analysis should follow design. You already know the model when you design the experiment. But sometimes experiments are carried out in order to distinguish between two models, and then the same procedures would be of use. So here's AIC. Here's the formula for AIC. It's amazingly simple. It's based on the log likelihood. The log likelihood. And it's the likelihood of the model given the data. Plus 2k. So you can think of it as having two parts. Now this formula sort of popped out of an analysis, a theoretical analysis in which a criterion was searched for that minimizes the loss of information when fitting a model to data. And the model that popped out, the formula that popped out was this one, and it's very simple. It's minus twice the log likelihood plus 2k. So the log likelihood is this part, and 2k is the other part. And so generally, if you fit more parameters, as I've shown you, the higher the log likelihood, or the lower the negative log likelihood. But at the same time, the higher the number of parameters, the larger this term. And the goal is to minimize the negative log likelihood plus 2k. In other words, the best model is the one that has the lowest AIC score. And so fitting more parameters lowers this, but fitting more parameters increases that. So these two components trade off. Now I want to stress it. The best way to interpret this is that it's sort of log likelihood with a penalty. But that's the interpretation. It wasn't invented to have a penalty. It was invented as a quantity to minimize loss of information when fitting models to data. So it acts like a penalty, and it's a good way to interpret it. As with log likelihood, what matters is not the AIC score itself, but the difference between AIC scores for different models. So AIC is an estimate of the expected distance or information loss between the fitted model and the true model. It is a little bit like a cross-validation score. It is a kind of prediction error. And as I said, there are two reasons why a model fitted to data might depart from the truth. One is that if it contains too few parameters, it'll be biased and predict poorly as a consequence. But if it has too many parameters, even though it will have lower bias, it will have higher variance. The more parameters you try to fit, the worse is your estimate of each of those parameters. AIC trades those things off. It doesn't give you the true model, it gives you the best model. Does that make sense? So here's an example of its use. Predicting numbers of species of ants in different habitats, latitudes, and elevation. So some science has gone into the choice of variables, but no science is predicting the effects of habitat, latitude, or elevation. So we're going to do a little bit of data dredging to try and figure out which model is actually best. And we're going to use the dredge command in the mu-min package, which is the one we'll try this week in the workshop. And the way the method works is that we fit a model, which is the full model that contains all the terms we want to include. And in this case, I've included all the main effects and their interactions. And then this model is the argument for the command dredge, which does an exhaustive search. And so the more complicated your model is, the longer dredge will take. So this is dredge's strategy, just fit all the models. And what you get out of it is a model selection table where all the models are listed, and I've only got a subset of them shown that will fit on the page. The log likelihood, the AIC, the delta AIC, which is the difference between the best model AIC and the AIC of each model. And then something called the weight, which I'll talk about a little bit. And this quantity here, df, which is actually the k in the equation for the AIC score. And the way the table works is the intercept, elevation, habitat, latitude, elevation by habitat interaction, elevation by latitude interaction, habitat by latitude interaction, and then the three-way interaction. And for a continuous trait, it gives you the coefficient estimated in that model. And for a categorical trait, it just puts a little mark there saying it's in. So the best model included an intercept, elevation, habitat, latitude, and no interactions. So it included the three main effects and no interactions. Dredge, as I said, fits all the models, but not quite. It obeys hierarchy. So an effect, a main effect, the variable is never tested against in a model that does not include an intercept. And no two-way interactions are tested without the main effects also in the model. And the three-way, the model with the three-way interaction must include all the two-way interactions and the main effects. So that's a property of testing in sequential hypothesis testing in linear models and generalized linear models as well. And k is 5 for this model because there are three variables that entered the model, plus an intercept, which is another parameter to estimate. And the number is 5 because you also have to estimate the variance of the residuals. So that's counted as a parameter in this model. So the best model wasn't the simplest model. The simplest model fits just an intercept. It's not even on this page. So there's the best model. Habitat, latitude, elevation, no interaction. I threw it into a linear model, and it turns out in a linear model, all of these terms are statistically significant. But I wouldn't pay any attention to these p-values. First of all, because it's a summary table, not an ANOVA. But secondly, because this is the outcome of a data dredging exercise, so the p-values are absolutely erroneous. This is just the residuals versus the fitted values to show you that the fit is actually reasonably good. Fit to assumptions is reasonably good. So here's another way of looking at the results. So here's the plot of delta AIC against the number of model parameters. And the best model is this one here with 5 parameters. And so then the question is, okay, that was our best model, but what other models are there that fit the data nearly equally well? And this is sort of the conventional way of comparing AIC scores. So the AIC score doesn't matter so much as the difference, the AIC difference. That's what delta AIC is. And so this value here is the difference between the AIC of this 4-parameter model and the best model. So every model is now compared against the best. And the convention is to include any model in your confidence set that has some support. So any model which is within 2 AIC units of the best model is basically indistinguishable from it. And any model that has somewhere on the order of 7 or less has less support, but nevertheless some support. And so at some point we can cut this off and say these are all the models that fit the data nearly equally well, or at least have some support from the data. And that represents our confidence set of models. Here's another way of applying the data, all the terms along here, and the delta AIC scores. And so some cutoff on the order of maybe 7, an AIC difference of 7 would say, here's 7, draw a line across, these are all the models that should be retained as under consideration and might be they have some support. 10 or greater, just ignore. So we can ignore all these models. Another way to figure out this sort of confidence set of models, all the models that have some support, is to use a measure that's somewhat analogous to a 95% confidence interval, and that's to use cumulative model weights. So these are the terms here. And a weight is sort of the weight of evidence that this is the best model. So this measures a quantitative, gives you a quantitative score measuring the amount of support and all the models, the weights for all the models in the long list that were fitted, sum to 1. So it behaves like a proportion almost. So they measure support that a given model is the best model, assuming that the best model is somewhere in this list. And so the weight of evidence is highest for the best model. But the weight of evidence is not much less for the second best model, and so on. But then the numbers start to get smaller and smaller. And so one way to include or figure out the set of models that are part of this 95% confidence set is to include all of the models whose cumulative weights, so order them by their weights and then accumulate them and keep everything that is below 0.95. So again, that would include all of these values here. And we'll try this ourselves in the workshop this week. Okay, how do we feel about this? This is the basis of AIC, and it has some popularity. If all you want is to fit a model that allows you to predict, the number of salmon coming back next year, then all of the models that have relatively small AIC differences, consider that they predict reasonably well and should be considered. There's no reason to get carried away over the fact that you found the best model, because the second best is actually pretty good too. And so it's the third best, in fact, and this might include as many as 10 models. But often what we want to get from the model fitting exercise is actually we want to figure out that set of variables that is actually the cause of variation in the model. We don't want to just be able to predict how many salmon come back next year. We want to know the variables that influence how many salmon come back. And that's starting to go beyond prediction into, causation. But keep in mind, regression isn't causation. That you'll never really be absolutely sure about which variables are the actual cause, how many salmon come back next year, unless you do an experiment. There are other methods. There's another procedure in the maths library called STEP AIC, which again is another strategy for finding the best model. And I guess these are the two that I would recommend giving a try if you ever do model fitting, and we'll try them in the lab this week. So they both do fairly exhaustive searches, but both of them obey the restrictions that squared terms aren't fitted unless the unsquared term is also in the model. Two-way interaction isn't fitted unless both the magnitudes are also present, and so on. So it's exhaustive, but it's also intelligent. But we're still data dredging. So this seems reasonable. It's not very different from the cross-validation approach that I used at the very beginning, except we have more, we have some theory to give us an idea of what support actually means for models of different complexity. But at the end is that we arrive at a model and a confidence set of models that do nearly as good a job. And in this process, we've sort of done something somewhat analogous to estimation, I think, where we would calculate an estimate like x bar and then have a confidence interval around it. Now we've calculated our best model and we have a confidence set of models that are not ruled out. But in this process of finding a best model, we didn't test any hypotheses. There was no null hypothesis at all. So one answer to a question that came up is, what do you do when your null model is not rejected but it's silly? Well, don't even worry about that. Use a procedure that doesn't do hypothesis testing in the first place. No p-value. I got no p-value out of this. And it frequently happens that if you apply an AIC criteria and find your best model, and then fit this model to the data using LM, that some of the terms, well, first of all, the p-values are meaningless anyway, but if you looked at the p-values, you might often find that some of the terms aren't statistically significant, and they wouldn't actually be retained if you used stepwise regression. But what does that matter? Our criterion isn't to have only significant terms, which is a little bit weird anyway, given that we can't trust the significance levels from a sort of a data dredging procedure. But we have no p-value at all. We had a criterion. Our criterion was we want a model that predicts well. So this is it. Or this is one of them. Anyway, there are other criteria that have also been developed, and there's much discussion about which one is the best, but this one is certainly pretty straightforward. It's very similar to cross-validation. No model is really formally rejected in the same way that a 95% confidence interval doesn't actually reject values outside there, they're just less plausible. We haven't tested a hypothesis, so we're not really rejecting anything. Your best model isn't necessarily the true model. All we know is that this procedure in the long run gets us the least information lost when trying to fit a model to data. So try to avoid assuming that this best model that ends up from the procedure is actually the truth somehow. Because we don't actually know what the true model is, and we never will. Unless we, collect an infinite sample size. But it does a pretty good job. It balances this bias variance trade-off of the two quantities that make predictions worse. And we've incorporated model uncertainty, not just coefficient uncertainty. The model itself is, we admit that the model itself, that we don't actually know what it is, but we have an idea that it's the most plausible set is this one here. Finally, I just want to mention something called multi-model inference, which you may have heard. And sometimes what people are interested in is to estimate a parameter based on a set of models that somehow takes their uncertainty into account. Like, I want to know what the effective latitude actually is. But I don't know which model is actually best, even if latitude is included in all of them. What is the effective latitude? Like, what's that coefficient? What multi-model inference does is it actually basically takes an average of the coefficients across all those models weighted by the amount of support for each of those models. That's what multi-model inference is, and it avoids the need to base your estimate of a coefficient solely upon the best model. It somehow takes into account the uncertainty about which model is actually the best in the long run. Okay, so I'm just giving you a source of information. I got a couple of books here on model selection and multi-model inference. So this is Burnham and Anderson, which is sort of the Bible on this. But Anderson has written a much more slender, readable, and easier to understand version, and so I would perhaps start there. I'm not going to talk about multi-model inference, but you'll hear about it, and you heard it here first. So a lot of the uses of these information criteria are for data dredging. We don't really have a theory that predicts anything very specific, and we're just sort of searching among the various models to try and come up with something that works. But this approach can also be used to test competing conceptual models or theoretical models, and I'm going to show you one example now. And when you have, say, two alternative models and you're trying to test them, neither of them is declared the null model. They're both models that are under consideration, and we just want to know which one is better and how much better it is. So this is a stickleback example. I work on stickleback. And it's a time series that was gathered by Mike Bell of a sort of a fossil stickleback species, Gasterosteus dorissus. And this is now, and this is about 8,000 years ago. So time equals 0 corresponds to the first appearance of a highly armored stickleback in the fossil record. And what Mike Bell has done is he's sort of looked at these very fine stratigraphic layers and lifted them off, and then measured the amount of armor, or dorsal spines, pterygophores, and pelvic spine. So he's actually measuring these fossil specimens, which are just sort of laid down, and look at the fine scale of measurement in this case. So each sample, each dot is, just 100 years or so. So this is an amazingly fine record, fossil record. You'll see very few fossil records as with so few gaps anywhere on Earth. But what he observed was that each of these traits showed a pattern of decline. And that's pretty characteristic in stickleback. After colonization of fresh water, the armor evolves to lower and lower levels. And so that's true for each of these traits. And what Mike Bell did was he measured the change from here to here, from here to here, from here to here, from here to here. So he had all these changes, and he compared each of those changes to a null model called a random walk, where the probability of going this way and this way is the same, and where the distribution of step sizes follows a normal distribution with a mean of 0 and a variance that's estimated from the data. So Mike Bell tested that null model and was unable to reject it. So P was greater than 0.05, and he published this. And looking at the data, Gene Hunt said that's a silly null. Not only is that a silly null model, but this is a really weak way of analyzing data like this. Why have a null hypothesis in the first place? Why don't we think about comparing a model of a random walk to a different kind of model? Said that. And the model that is often used in modeling data on phylogenetic trees is, I think of it as adaptive peak shift model. So the neutral random walk basically is as I described, a mean step size of 0, a variance that's estimated from the data. But an adaptive peak shift, I don't know if I have a depiction of it, but this is what it kind of looks like, that there's an optimum somewhere, and that gradually over time the population might oscillate in getting there, but it eventually gets there and equilibrates. So that was the other model that Gene Hunt tested with these data. And there's two parameters in the neutral random walk: the initial trait mean and the variance in step size every generation. And then this the adaptive peak shift model, there are 4 parameters. Those same two, but then also the position of this optimum, and then the strength, the pull, how strong selection is in bringing a population toward that optimum. So here are the 3 traits, and the 2 models being compared. Their log likelihoods, the number of parameters k, and then the AIC score, AIC weights. And the finding was that there's far more support for the alternative model than for the random walk model, which is completely the opposite conclusion reached by Mike Bell in his original analysis. So the IKK weights, basically you take the amount of support for each of the models and apportion them into a quantity that sums to 1 across all the models being fitted. And so you can kind of think of the 95% confidence set of models includes the adaptive model and not the neutral model by this criteria. So this was kind of a cool paper because it was one of the first instances that I know of, at least in the evolution literature that I read, where 2 models had been compared for an evolutionary process and neither of them was null. And yet a conclusion was arrived at as to which one was clearly the best model in this case. And the lead author of the paper, Gene Hunt, he wrote to Mike Bell and said, let's do it this way instead. And that's what produced this second paper and this table of results. And after spending a great deal of time in this paper explaining why this approach was superior to a null hypothesis testing approach, they abandoned the high ground and carried out a log likelihood ratio test, assuming that this was the null hypothesis and this the alternative. And actually, this kind of exercise is like, I just told you that this whole approach doesn't have null hypotheses at all. Nothing is rejected, etc., etc. And now look what they're doing. But the reason why I'm pointing this out rather than just eradicating it and pretending that you should see this is that even using the conventional statistical approach, using a null and alternative hypothesis, was more powerful than the one that Mike Bell used, where he did not have an alternative hypothesis. He just had a null hypothesis. Whereas with a log likelihood ratio test, you need 2 hypotheses to be compared. And so I show this just to make the point that having more than one hypothesis can be a really good idea if you sit down and think about what theory might predict. Where you can come up with a couple of alternatives that, even if you're using null hypothesis significance testing, you're better off having more than one hypothesis. And that's going to be a theme in a later reading and in discussion. Oh yeah, I just said that. So everything but the null hypothesis is probably the worst way to proceed. Having 2 models is a much better way of proceeding. And abandoning null hypothesis testing altogether and measuring the degree of support for each of the models is probably the better approach in this case. So, just to summarize then, stepwise elimination of terms and null hypothesis significance testing is no longer regarded as the ideal approach for model selection. So abandon crawling, never mind the inadequate model approach using regression, stepwise regression. And we learned a lot of reasons why this approach can be problematic. But using the approach requires that you give up p-values. Can you do that? Are you strong enough? The reading next week will try to convince you that this should be done on first principles. But at the same time, we're still data dredging, and these methods work best when thoughtful science is applied beforehand to sort of outline the candidate models that make sense. So minimize the data dredging, and the second example of evolution in stickleback was meant to be an example of thoughtful science, coming up with a couple of simple alternative models and then applying this approach. No data dredging involved whatsoever. Working with a set of models that fit the data about equally well rather than one best model takes account of the fact that there really is model uncertainty, and that's something that these methods give you that the stepwise approach does not. But if you really want to know something about causation, do an experiment then. But at the same time, we want to data dredge. We did this study. We measured so many variables. Come on, we really want to have a look. And one reason for doing so is that we might actually find something new, something that our theory didn't anticipate. So how do we deal with that? Well, that actually came up already in the presentation and the discussion. And a simple way to describe it is be honest. And one way to do that is to have your paper, the analysis in your paper, have two parts. The first part, here's my test of the models that I did this study for. And then the second half is, now I'm just exploring the data. I'm doing data dredging. And as long as we know that that's where a particular result emerged from, then we can take that into account. We won't take it too seriously, but there might be something sufficiently interesting in there that it might be worth someone repeating your study and seeing if the discovery is repeated. So don't throw away your data. Do both, test and explore. That just make it clear when you're doing one and when you're doing the other. One example of the benefits of exploring data is this one here. So, I gotta go. Here's a model fitted to, this is, I got this from Andrew Trites. Female fur seals, body length, female age. You might just put a simple curve through this and say that's the relationship between weight and age. But if you actually look carefully, the relationship looks like this. Incredibly complicated model. This is whatever, 20th order polynomial. And what's going on is that when the females haul themselves out on land, they actually get longer. Their skeleton actually stretches. They do get longer, and then when they go back to the water after the breeding season is over, their vertebrae get closer together again. And that pattern would have been missed entirely if all we did was fit what we think of as a characteristic growth curve. So by all means, explore your data. Here's the paper next week. The Earth is round, P is less than 0.05. This is sarcasm, folks. I have two presenters looking for two moderators. Come up and tell me if you'd like to do this one, or we'll find you. Are you ready?
Yes.
You're supposed to do this one? Okay, I'll check my calendar just to make sure. Okay, thanks everyone.